Hello, welcome everyone. Welcome to this particular e-school on climate science and policy organized by Interdisciplinary Program in Climate Studies at IIT Bombay. So basically we have this interdisciplinary program, and every year we conduct a summer school for the students to get to know about our research and other activities. The basic idea is to first disseminate the knowledge and also attract the students for PhD in climate studies and climate science area. uh, so every since this is seventh time we are running this, but this is special this time because we are going live online this time. Last six were process was different. We used to conduct, we used to ask for the applications, we used to scrutinize the applications from the students only, and then we used to select around 25 to 30 students across country, and 5 day continuous rigorous summer school we used to have. But COVID has now given this particular opportunity to go live, and this time we are open for everyone. So we have around 1300 plus registrations for this particular e-school, so we are very happy about it. And basically these videos you can will be there on the YouTube, so you can come back to it, or you can share further if you like. So I would like to introduce today's speakers. So first we have inauguration. So I have with me Professor Parthasarthi, who is a, professor in humanities and social sciences and a convener for interdisciplinary program in climate studies. So welcome, Professor Parthasarthi. Uh, then I have with me Shri Narendra Tokeji, who is basically NV's coordinator, director, environmental department, government of Maharashtra, and also in charge of Maharashtra State Knowledge Management Center on climate change. Welcome, sir, for joining us for the inauguration. And we have our first speaker today, who is also co-coordinator of this particular school e-school activity, Professor Subimal Ghosh, who is a professor in civil engineering. So, welcome, Professor Ghosh. Uh, so, uh, I request Professor Parthasarthi to share his thoughts about this particular activity and introduce our IDP climate study.
Um, just 1 second. Um, Thank you, Professor Pradeep Kalwar. Can you all see my screen? Yeah. So you
Yes.
can. Yeah. Okay. Thank you, Professor Kalwar. Uh, and on behalf of the IDP in Climate Studies and on behalf of IIT Bombay, let me welcome you all for the seventh summer school on climate science and policy. We are overwhelmed by the response this year. As Professor Kalbar was saying earlier, we used to have it physically in IIT Bombay, usually in the month of July. And the whole objective of this summer school is to catch them young. So, get undergraduate and postgraduate students from around the country, introduce them to different topics in climate science and policy, with the objective that these students may get to know more about what exactly is involved in climate science, climate social science, and policy, and then take it up for higher education and for their own careers. So I think Mr. Narendra Toke is here, Director of Envis and Environmental Department. So he will appreciate that India as a country and the state of Maharashtra as well as other states, we need a lot more capacity in climate studies. So it's an area in which a lot of expertise is required, and government institutions across India are setting up specialized departments to address climate challenges. And we need more and more people to carry out what we call as strategic research in the area of climate change. And therefore, we started on a small scale, but we are very happy to know the huge response this time, not just from students, but a lot of people from NGOs, from government, and from other sectors, from the private sector as well. Let me join Professor Kalbar in welcoming Mr. Toke. He also heads, as Professor Kalbar mentioned, the State Knowledge Management Center on Climate Change. And IIT Bombay and the IDP in Climate Studies are very happy to associate with the SKMCCC. We had a meeting last week, and we look forward to working closely with the government of Maharashtra to carry out strategic research and provide policy advice on climate challenges. And Professor Subimal Ghosh, who will give the first lecture of this series. He's been with the IDP ever since the beginning, and he's one of those uh, who's done a lot of work, especially on the Indian monsoon and the impact of climate science, climate change, specifically for the Indian context, focusing on the monsoon. And his research is very well known and has won a lot of awards. So we are very happy that he's able to start off this summer school. So the basic idea of the summer school is to provide an introduction to diverse topics that are relevant for understanding climate change, the impacts of climate change, and for designing policies to address these challenges. And towards that objective, what we try to do is to bring together a group of our faculty members associated with the IDP in Climate Studies at IIT Bombay, and uh, they will not just talk about issues that are relevant for India, but they will draw upon their own research in these areas. So these are live research projects from which they are drawing upon, and we've also designed it in such a way that while we try to create an awareness of the scientific knowledge related to these topics that we are covering for the summer school, we're also trying to simplify them for a more general audience so that they become attracted to a career and maybe higher education in climate studies. So I'll spend a few minutes introducing you to what the IDP is. Those of you who are interested to know more, either to work with us, to study with us, to collaborate with us, are free to contact us. So we started about 8 years ago in 2012, and it's one of the first PhD programs in climate studies, and we have about 31 faculty members from 11 different departments across management, social sciences, and engineering. And we work across the different pillars of climate science and policy identified in the IPCC reports, including climate science, the impacts, vulnerability, adaptation to climate change, mitigation, and policy. Over 50 PhD students are currently enrolled, and more than 15 students have already graduated. And we have about 6 to 7 postdoctoral fellows also working in various projects in our IDP. So the primary mission is to foster a fundamental understanding, but we do so not just from an academic perspective, but from a more strategic perspective, which is why we are saying that our analysis of climate science and solutions comes from a focus on specific problems of relevance to India. And in achieving this mission, our objective is education and capacity building, which is through the PhD program, but also through what we call as CEP, continuing education programs, and this summer school itself. So our primary objective has always been to produce strategic knowledge that is of value in not just understanding climate related impacts, but how to design solutions and policy recommendations to address these challenges in diverse sectors across health, urban, coastal, water, flooding, and so on. The number of students enrolling for various PhD level courses has been steadily going up. We've also last year started an undergraduate program, an introduction to climate studies, which has proved to be extremely popular. On the right side of the screen, you can see a number of courses, existing courses which have been repurposed, and new courses related to climate sciences that we are offering us to our PhD students. So the number of PhD students has been increasing, and the number of faculty members as well as the departments they hail from are increasing. All of these come together as associate faculty in this IDP in climate studies. And the students who graduated have been placed in universities in India and abroad as faculty members, as postdoctoral scholars. They're also working in government agencies and also in industry in various capacities. We're very happy that a lot of high impact publications have already emerged from the research we've been doing over the last 8 years. And a lot of them have not just been cited within academia, but many of them have been publicized in the media, which has found our findings, our research findings, very useful in making the general public aware of the challenges of climate change. Um, this particular summer school is sponsored by what is called as the Center of Excellence in Climate Studies. So this is funded by the Government of India, Department of Science and Technology, under the National Mission on Strategic Knowledge for Climate Change, under the National Action Plan on Climate Change. So the first tranche of projects were completed in 2018 under this Center for Excellence across mitigation, science, policy, vulnerability, and adaptation. Uh, so As part of this, we focused, as I've been saying earlier, on climate science, on mitigation and policy, as well as vulnerability assessment and adaptation, all three major pillars, which are very important for addressing climate challenges. And we've been involved, as I said earlier, both in capacity building and in producing strategic knowledge. The focus areas are mentioned here, but those of you who are more interested can look up the IDP website for more details on these areas of research. We also have a major multi-partner project involving more than 20 partners from across India. This is the National Carbonaceous Aerosols Program, headed by Professor Chandra Venkatraman, and Professor Subimal Ghosh is also a member of this team. So this particular project across India uh, not just seeks to assess the distribution of carbonaceous aerosols across different sectors and the magnitude of this distribution, the emissions, but also to see how these impact precipitation and rainfall patterns in different parts of India. So this is a very highly significant project and very valued by government and researchers for the kind of results that it can show. That's already producing and it is likely to produce in the next few years. The second phase of the Center of Excellence was funded by the DST, the Department of Science and Technology, from 2019 onwards. And again, you can see that we are focusing on climate impacts, kind of vulnerability that people in coastal areas, in agriculture, in other sectors are exposed to. So we're also looking at science and modeling, especially land atmosphere models. Uh, Linking to the earlier NCAP project, there's a focus on aerosol forcing also. So there are 14 projects in this particular center. And again, we've been specifically asked by the DST to convert this research into strategic research that can contribute to policy making at the national and regional level. Other than this, there are a number of other projects that our faculty members are involved in across social sciences, policy. Uh, we are also involved in some of the state action plans on climate change in Rajasthan. We're working with the Maharashtra government, working on coastal areas, on flooding, on agriculture. So pretty much all different sectors are covered by us. These are some of the faculty areas of expertise. I won't go into them in detail, but you can see again they cover all the different pillars of climate science and policy, and you'll get more details of these on our website. Uh, Finally, we are working very closely with different stakeholders of government in different parts of India to provide research-based advice. We have established MOUs with many national and international institutions working on climate issues for data sharing and research collaboration. We have a number of training initiatives, including this summer school, and we've developed a number of modules on different topics for government officials at different levels, for private sector and for NGOs, and also a number of workshops on specialized themes have been organized by us. Okay. So I will now move over to show you a short video of what exactly we do in the IDP, and then we'll request Mr. Tokye to give his inaugural address. Thank you.
understand the climate system and to respond to climate change, a large interdisciplinary effort is needed, encompassing engineering, science, as well as social sciences. And this is the philosophy behind IIT Bombay's interdisciplinary program in climate studies, or climate IDP as we call it. Set up in January 2012, this is one of the first doctoral programs in India for education and research on climate change. It draws on varied expertise of multiple faculty members from more than 10 departments at IIT Bombay and offers a challenging curriculum and diverse opportunities for interdisciplinary research.
The climate system is composed of ocean, atmosphere, land, biosphere, and cryosphere, which are interconnected through complex processes like biogeochemical cycles, like small and large-scale motions of the atmosphere and ocean, and includes the formation of clouds, rainfall, and the occurrence of floods, of droughts, and other extreme events.
Climate change poses a serious threat to our planet. The anthropogenic factors like emissions from greenhouse gases, atmospheric pollutants, and aerosols are the primary reason for the changing climate. The historic increase in the carbon dioxide levels has led to a drastic increase in the temperature, triggering activities such as sea level rise, erratic rainfall, and glacier meltoff.
Thanks to a lot of space-based missions that we now have, we are able to get climate-related data variables, which provide an indispensable source of information to study about climate change. Now, the tons of data that get streamed from the satellites can be subjected to complicated algorithms and state-of-the-art data assimilation techniques that help study about the impact of climate change.
The fluid motions in ocean atmosphere influence the climate processes. Here at IIT Bombay, we use laboratory experiments, field expedition, computer simulations, and complex Earth system model to study and understand a variety of processes that influence climate change.
Given the present greenhouse gas concentration in the atmosphere, it will likely impact the climate variables in the near future. This is an unavoidable condition. Managing unavoidables is known as adaptation. You need to consider the climate change projections from climate science as well as the present socio-economic conditions as well as infrastructural condition in terms of vulnerability so that you can go for a sustainable management strategy.
Understanding the underlying processes that cause a sudden change in the climate, along with their impacts on human life, is the need of the hour. This should be augmented by strategic implementation of adaptation and mitigation policies.
So here we study policy instruments for addressing climate change mitigation in sectors like agriculture, energy, health, and so on. We also look at adaptation and what kind of policies are required to integrate adaptation with other kinds of developmental strategies.
It's very important for us to contain the impacts of climate change, that food production is not threatened, and that economic development can take place in a sustainable manner.
The Intergovernmental Panel on Climate Change, the IPCC, provides world governments with a clear view of the current state of knowledge. India has proposed an 8-point national action plan on climate change, and for scientific underpinning, the National Strategic Knowledge Mission on Climate Change has been launched. Climate IDP at IIT Bombay is associated with this program.
It's natural to ask the question, where would our students go in their careers? There are many opportunities related to climate prediction and planning, to hazard and risk analysis, to mitigation, carbon finance, green finance, and other such opportunities. Climate change is one of the most important global challenges, and the interdisciplinary program and climate studies at IIT Bombay serves the need of time.
Pradeep, you are muted.
Yeah, Mr. Toke, please go ahead. Yeah. So,
good evening. Hope I'm audible.
Yes.
Yeah. Good evening. I'm Narendra Toke, working as a Director Environment, Government of Maharashtra, and Head State Knowledge Management Center for Climate Change. As just we have seen the video which was presented right now by IIT IDP, and the climate change issue which was raised, and it first the action plan, national action plan on climate change, which came in 2008. It is on to be more precise, on 30th of June 2008. It was launched by our then honorable prime minister, and the 8 missions were considered. Those were the major missions which are related to climate change, which starts from national solar mission, national mission for enhanced energy efficiency, national water mission, and so on. And the most important mission was the national mission for strategic knowledge on climate change studies. That was the most important mission, what I feel, in the field of climate change. This entire climate change per se, it is not a particular subject that we can that the details are available and we can go into details and we can work out something. It is a multidisciplinary action needs to be carried out. Considering the national action plan which was formulated in the year 2008, Maharashtra is the state which has formulated our state council on climate change in same year, that is in September 2008. As a progressive and industrialized state, Maharashtra is always in advance in all climate change and environment protection per se. Here just I would like to add, before coming Water Act into force, the Water Act which came into force in entire country in 1974, prior to that, in 69, Maharashtra has developed a water pollution act per se. So likewise, in the same in climate change also, immediately after the mission which was launched by Government of India, Maharashtra has formulated the State Council on Climate Change in September 2008, and the adaptation action plan, which was decided, the deliberations took place in interdepartment of all the department of government of Maharashtra, and it was decided in 2009 to have a state action plan, adaptation action plan on climate change, and accordingly the work was allotted to TERI, the Research Institute, Pioneer Research Institute, and accordingly the state action plan, adaptation action plan, was prepared and submitted to government of Maharashtra in 2014. And a lot of deliberations which took place, so many actions were involved, and the action plan which was formulated, which was the 50 recommendations which have come from that, the action plan, the 50 recommendations were given to state government to have action on various departments. See, it was a bit difficult to have this entire 50 action points at a time. So government has decided to have a state policy wherein 14 action plans have been prioritized. The action points were prioritized, and accordingly the policy which was prepared by government of Maharashtra in the year 2017, and accordingly 14 action points which were prioritized, and these were mainly focusing on the protection of forest, then promotion of solar water pumps per se, considering the agricultural state and agricultural economy, which is the backbone of entire economy of India, and the creation of another one of the climate proof villages. So adaptation basically was being considered as the topmost thing. The lot of research is being going on, lot of activities are being promoted. They to promote organic farming and market access for organic produce. See, what happens is many a times a research is being carried out that we have to have this such type of adaptation, then we will go for such type of crop. But non-availability of a market for a particular crop leads to another disaster. So this is what the effort which was taken here into account, and which was decided to promote organic farming and market access for organic farming. That was also one of the action point with in the priority action what we have taken. Then the stringent norms, basically for emission norms, which is once again related to GHGs. So that was also a top priority action which was considered, and rightly pointed out, and rightly it is being discussed now in the Paris Convention also, that to incorporate this, to reduce this GHG, that is NDC and SDGs. See, everything is correlated with every sort of action what we are doing. So we, as a Department of Environment, always telling that it is not anybody's duty; it is everybody's duty. So I as a person should first initiate the action, and accordingly the action points were formulated, and those have been discussed and communicated with every department. And Department of Government of Maharashtra has first took in January 2016. We took a residential workshop per se for all government department, wherein almost 17 government departments they have participated on this action plan per se. See, that time it was in the policy was being framed, but to have the dissemination of knowledge and to create an awareness in all government department, 17 departments they have participated, and around 40 officials of various government departments they have participated in that process. Then in February 17, we have again organized a workshop that is tackling climate change to forestry actions in the Maharashtra to increase the forest cover per se for reduction of GHGs also. Then in 18th February 20, we had a climate exchange dialogue, which took in government department. See, basically what is happening is every government department is working on certain actions on climate change, but there is no interdepartmental coordination per se. For that, we always are having a dialogue with all government departments to incorporate, to have a proper dialogue, and to incorporate the policies itself in the budget also. So now the revision in action plan is going on. Initially, it was targeted towards the 8 government departments, the priority actions. I'm not telling that this. I'm talking about the 50 actions points which were raised, which came out in the policy per se. That is related with all the government departments. But the priority actions which were identified as a 14 action point, those were with related to 8 departments. Further, to enhance that, this new the concept of NDC and SDGs, National Determined Contributions and Sustainable Development, considering SDGs, Sustainable Development Goal, we have added further more 4 departments wherein this transport and other sectors have been included, and this revision in action plan is in the process, and rightly pointed out by Mr. Parthasarthi that last week we had a meeting with Department of Science and Technology, wherein the details were discussed along with IDP, IIT Mumbai also. The research topics which we are also planning to have, a lot of work is already being conducted as far as energy sector is concerned and forest is concerned. So now what we have decided in internally, and we are planning to have the another sectors which we are planning to have some research activities needs to be carried out as far as GHG inventory and GHG emission is concerned. Those are related to industries and waste per se. Waste includes the solid waste also. That is one of the major contributors towards the GHGs and the most neglected part per se. So that the internal discussions are going on, and we are coming out with a policy, and we have taken a decision recently is that this whatever the action plan, the revision in action plan is being worked out, and it will come out in 6 months time or 7 months time per se, because of this COVID, which was actually scheduled to be, the draft was to be published in the month of August 2020, and which was to be supposed to be finalized and submitted to Ministry of Environment and Forest by December, but unfortunately due to this COVID it will get extended for another 7 months or so. So in that we are planning to have this whatever the action plan which we are preparing, we are going to circulate it to government department to include it into financial budget also, so that whatever the actions will be initiated at a respective government department, a financial allocation will be done according to the priorities which have been decided by government of Maharashtra as far as climate change. So that's what I said initially. Everybody is doing something, this or that, for climate change, but this needs to be incorporated in proper fashion. So this we are working out, and we are planning to have it in the budget itself only, then accordingly the priority will be given. Definitely the government will take a call, and the Chief Secretary, Honorable Chief Secretary of Government of Maharashtra is the steering committee chaired by Honorable Chief Secretary. Fortunately, we have got a very good, dynamic, versatile Environment Minister, Mr. Aditya Thackeray, who is very proactive in environment protection and climate change. Shortly, a number of things will come. Then our Environment Secretary, Mrs. Manisha Meskar Patankar, she is also very proactive in environment per se, the tree conserve, and so many activities are going on. So in due course of time, definitely we would like to have an association with IIT Mumbai to have to come up with the research topics, and the other institutes like NEERI, BNHS, all institutes which are pioneer in climate change studies per se. We are going to have a collaboration with them, and definitely a good action plan. See, the action plan is there now. We need to work out adaptation and mitigation also, because a lot of discussions are taking place, a lot of discussions are going on, a lot of deliberations are going on, and the research institutes like IIT, NEERI, BNHS, they will play a major role for guiding the government per se, for making the policy and implementation of policy. See, we are good, we Indians are good in making policies, but the problem lies with implementation. That's what I feel. The policies are good, but the implementation. So, what we have decided now in this coming revision in action plan, the implementation per se will be allotted, will be related to, say, finance. If it is related to finance, then definitely the implementation will be in proper manner. So this is what is at the government level we are going, and I would like to thank IDP, IIT Mumbai, for giving an opportunity for government to just disseminate the information what basically government Maharashtra is working on that. And this is what is the e-school, where the undergraduates and postgraduates, they will really think of whatever the activities, and we require their support also in mitigating adaptation and mitigation of climate change. Thank you. Thank you on behalf of Government of Maharashtra. I would like to thank everybody. Thank you.
Thank you, Mr. Toke. Thanks for nice overview of the government activities and initiatives. And we at IDP Climate Studies will look forward for collaboration in coming duration. Thank you. Thank you very much for joining us for this inauguration. Also, I thank Professor Parthasarathy for joining for the inauguration. I announce inauguration as concluded. Now I request uh, Sindhu to start the next session by Professor Ghosh.
Good evening, everybody. Sir, are you able to hear me?
Yeah.
Hello.
Go ahead.
Good. So, a warm welcome to all participants. This e-school will begin with Professor Subimal Ghosh's talk. Professor Ghosh is currently serving as a professor in Department of Civil Engineering, Center for Urban Science and Engineering, and Interdisciplinary Program in Climate Studies at IIT Bombay. He did his undergraduate studies from Jadavpur University and Masters and PhD from Indian Institute of Science, Bangalore. He has expertise in hydroclimatology, specifically in regional climate modeling, understanding of Indian monsoon and its variability, mesoscale hydrological modeling, water resources system, and simulating land surface feedbacks to climate. He's a lead author of IPCC Assessment Report 6, Working Group 1, focusing on climate science. He's the recipient of the prestigious Shanti Swaroop Bhatnagar Prize, Swarna Jayanti Fellowship, Indian National Science Academy Young Scientist Award, Indian National Academy of Engineers Young Engineer Award, National Academy of Science India Young Scientist Award, and India Science Congress Association Young Scientist Award. He has more than 90 journal publications, which include Nature Climate Change, Nature Communications, Science Advances, Geophysical Research Letters, Environmental Research Letters, Water Resources Research, etc. The topic of his talk today is land-atmosphere interactions in Indian summer monsoon. Over to you, Dr. Subimal Ghosh.
Thank you, Shiva, for such a kind and nice introduction. So I'll start sharing my screen. Just a moment. Okay, I'll probably share. Is my screen visible, Shiva? Is the screen visible, Shiva?
Yes, sir. Yes, sir. It's visible.
Okay, great. Thanks. So yes, my topic is land atmosphere interactions in Indian monsoon. So when you are talking about land atmosphere interaction, let us try to understand this topic slowly, and then we'll go into the key. I mean the works which we did in land atmosphere interactions. So when you are talking about land atmosphere interaction, what does it mean? Remember here, land comes first before atmosphere. So when you're talking about any kind of impacts of atmospheric change or climate change, what we essentially mention is that, of course, there are a lot of changes which are taking place in atmospheric processes. And the impacts of those changes on land, let's say on water availability, let's say if there is a change in precipitation that will impact hydrologic processes such as soil moisture, such as evapotranspiration, such as groundwater, and so on and so forth. But what I'm trying to mention here is that, okay, if there are changes in land, the changes can be natural changes or the changes which are made by humans, let's say in terms of irrigation, let's say in terms of land use, land cover change. Will that have any feedback to the atmospheric processes or not? So any change that is being made on land by naturally or through human interventions, do they have the potential to perturb the atmospheric processes or not? And if they can perturb, that is known as land atmosphere interactions. So it actually talks about from land to atmosphere.
So, Professor Ghosh, I think your PPT is not
Yeah,
on.
the PPT is not visible.
PPT is not visible.
Only your desktop like
Okay. So I'll try again. Share screen. Application window. Is it coming now?
not yet. So,
Yeah,
yeah,
now
yeah,
it's
yeah.
coming.
Now it's
Yes,
coming. Yeah.
now it's
Okay.
coming. Okay,
Yes.
good.
So what I was trying to mention is that, when you're talking about land atmosphere interaction, we're talking about the land processes that have potential to affect the atmospheric processes. So this is what we meant by land atmosphere interactions. So, and Indian monsoon. So let us try to understand what does it mean by monsoon. So if you remember, we read it in the 7th or 8th standard geography book that in globally there are actually three cells. One is Hadley cell. So essentially this is our globe, and this is the equatorial region. This equatorial region has higher temperature, and because it has higher temperature, that results into trade winds like this. These are essentially the northeast trade winds and these are southeast trade winds. And when these both trade winds converge, that results into Inter-Tropical Convergence Zone or ITCZ. These are essentially high rainfall band. Now, yes. Now during the summer time, what happens? Sun moves northward. So the ITCZ also moves northward, like it is moving northward. And during the south, it comes downward. These are essentially the seasonal changes. Now what happens? Let's say during the summer months of northern hemisphere, which are essentially June, July, August. For India, it's slightly different because I'll come to that. But so for northern hemisphere, the June, July, August, September, these are essentially the summer months. And during that time, this ITCZ moves northward. India is somewhere here. When ITCZ moves northward, the entire Indian region, because of the northward movement of ITCZ, receives lot of rainfall, and that is known as monsoon, summer monsoon months. Monsoon means seasonal, so these are essentially summer monsoon months: June, July, August, and September. Because of the northward movement of ITCZ, we receive lot of rainfall. And during the winter time, as ITCZ moves downward or southward, we don't receive much of rainfall. So this is what is the mechanism of monsoon. Now, if you consider this monsoon is affected by multiple factors, starting with El-Nino Southern Oscillations. This is almost known to everybody now, because every year at the starting of monsoon, you'll find it in newspaper. El-Nino Southern Oscillation happens in Pacific Ocean, the equatorial Pacific Ocean, where there is a certain region known as Nino 3 and Nino 4, in between Nino 3.4. So these are essentially the regions that gets warm up during the El Nino times. So during El Nino years, this region gets, the sea surface temperature over this region increases, and that results into decrease in Indian monsoon rainfall. So typically during the El Nino years, Indian monsoon rainfall is lower. At the same time, there is something which is known as Indian Ocean Dipole moment. So Indian Ocean Dipole moment means in the Indian Ocean, again there are two regions, western regions and eastern regions. When western regions gets warmer, that results into more rainfall. So even if there is an El Nino year, if Indian Ocean Dipole, and as per Indian Ocean Dipole moment, if the western side is warmer, we'll still get a good rainfall. So El Nino and Indian Ocean Dipole moment, they work together to affect Indian monsoon rainfall. So this is about interannual variations. That means, so Indian monsoon has interannual variations in the sense that some of the years we have very good rainfall, some of the years we don't have very good rainfall. And this interannual variations of rainfall is affected mostly by El-Nino Southern Oscillations and Indian Ocean Dipole moment. Of course, there are other factors like Atlantic Nino and so on. Now, Indian monsoon also has a very nice multi-decadal variations. So let's say if you pick up the low frequency variability of Indian monsoon rainfall, you'll find a very nice periodicity of 65 years, around 65 years. And if you check the Atlantic Ocean sea surface temperature, it also has a very nice periodicity of 65 years. And there were papers or articles that mentions that Atlantic Ocean sea surface temperature, the multi-decadal oscillations of that actually affects the Indian monsoon multi-decadal oscillations in through the Eurasian snow cover and so on. So essentially, there is another thing, Atlantic multi-decadal oscillations, that affects Indian monsoon at multi-decadal scale. Now, at the same time, Indian monsoon also has an intraseasonal behavior. Intraseasonal behavior means during the entire monsoon months, that means June, July, August, September, all these 122 days, during all the days we don't receive very high rainfall. During some period we receive very high rainfalls, which are known as active period, followed by some of the days during which we don't receive very good rainfall, which are known as break period. And these active and break oscillations are being governed by monsoon intraseasonal oscillation or MISO and Madden-Julian oscillation, which are actually happening at the equatorial region. So Madden-Julian oscillations and monsoon intraseasonal oscillation actually affects the intraseasonal variations of Indian monsoon rainfall. And at the same time, Indian monsoon has variability, spatial variability due to orography. We all know that in the Western Ghat regions, when the moisture weighted wind hits the windward side of the Western Ghats, this is very high rainfall, and leeward side of the Western Ghats do not receive that much of rainfall. So orography plays another role, and of course vegetation. There is a huge variety of variability, spatial heterogeneity of vegetation that's there over the Indian region, that also affects the Indian monsoon. So these are essentially a very complicated phenomena, simply because each of these factors like El-Nino Southern Oscillations, Indian Ocean Dipole moment, Atlantic multi-decadal oscillations, all of them are extremely difficult to understand. And you can now think of Indian monsoon, which are affected by all of them together at different scales. So Indian monsoon is one of the most challenging tasks in meteorology is to simulate Indian monsoon, and hence it's really challenging. And we need to understand a lot of things about Indian monsoon to really understand how to really improve the simulations. So let us try to understand what we do for Indian monsoon simulations. So for Indian monsoon simulations, Government of India, Ministry of Earth Science has one of the there are multiple models, but one of the model is operational model, that is known as Climate Forecast System version 2. So it was initially developed by NSET, and then monsoon scientists have further modified to make it more appropriate for Indian monsoon. And this model is now at present used for operational monsoon forecast. So let's say if you're talking about seasonal monsoon prediction or interseasonal predictions and so on, these are essentially done by either by CFS V2, that is the Climate Forecast System version 2, or its atmospheric component, which is known as GFS. So this climate forecast system version 2 is a coupled model, and its atmospheric component is known as GFS. Now, there is a major problem in climate forecast system version 2. So if you consider the operational monsoon model for India, it has a major limitation. The major limitation is that you can see this yellow and red bands. GPCP is an observed data, or ERA interim is a semi-observed data. So essentially, what you can find is that, you know, the simulated rainfall by CFSB2 has a very dry bias. That means it underestimates the Indian monsoon rainfall and overestimates the rainfall over the oceanic part. So remember, Indian landmass and Indian Ocean is always in a competition to receive the moisture. But what happens in this model is that they produce always lot of rainfall over the landmass, and over the ocean, and they produce quite a less rainfall over the landmass. So landmass always has a dry bias or lower rainfall. Now, this is one of the major problem of CFS version 2, and a lot of research are going on to really understand what are the reasons behind it and how to really take care of that. So, of course, you will now ask me the question, if CFSB2 is producing such a dry bias, how can we use it for operational prediction, or how can we continue with operational prediction, or how did we continue for last few years with operational prediction? So, there is a methodology. So, what we normally do is that you take the CFS version 2 simulations of monsoon rainfall and the observed monsoon rainfall, find out their difference in the mean, which we call as bias, correct the bias, and apply the bias correction for the predictions. So these is some kind of simple correction which we apply, and using that we do the prediction. But what we always miss is that this bias has a significant interannual variations. So one of our work, we have found that even if you consider the dry years and wet years, they have a different kind of biases. And when you have such a strong interannual variations even in the bias, then you cannot really just think of a fixed correction. And that is one of the challenge I feel. And hence we really need to understand in what way we can actually remove this sort of biases, not just by using statistical method, or not just by use a dynamical method, or think of probably a physics guided statistical approach, or more understanding about the model and improving the model with these understandings, which are not yet explored yet. So this is the idea. Now, the other important thing about Indian monsoon is the spatial variations. So spatial variations are there in extremes as well as for mean. So I'm just showing one of this figure. You can see this figure. This is taken from the monsoon page of IMD. This is this year's rainfall from 1st June to 16th August. So till yesterday, what was the rainfall? So you can see there are a lot of red spots. Red spots are essentially extremely deficit areas of rainfall, and there are a lot of blue spots. Blue spots means the extremely excess or large excess rainfall. So you can see on the one hand we have large excess areas, on the other hand we have deficit areas. So there is a mixture of large excess areas and the deficit areas, and that is one of the feature of Indian monsoon. It has huge spatial variability. That means the rainfall behavior of one region is quite different from another region. Now this is also consistent. I mean, this also happens in the rainfall extremes. Now we published a paper in 2012 in Nature Climate Change, where we have shown that the spatial variability has actually increased over last 50 years. And this is very important, because what we are trying to say is that the rainfall pattern of one region is becoming different from the rainfall pattern of its neighboring region. That means the spatial variability is kind of increasing. So what does it mean? Why? So because monsoon, we believe, it's a large scale process. It's affected by El-Nino Southern Oscillations, affected by Indian Ocean Dipole moments. It's driven by the movement of Inter-Tropical Convergence Zone. All are essentially large scale processes. But what is the reason because of which the rainfall over a small region is getting different from the rainfall of other regions? So we hypothesize in this paper that probably the local scale factors are playing major role. And in what way the local scale factors may play a major role? One can be urbanization, second can be the water management of human being, the third can be land use, land cover, and so on and so forth. So what we are trying to see here is that okay, yes, spatial variability of Indian monsoon rainfall is increasing. That means probably the local processes or land processes are playing a major role. And this is something which has been neglected in monsoon studies. Till 2014, there was no quantification of how much monsoon rainfall is getting originated from the land evapotranspiration. So we thought of, in 2012, we thought of, okay, let's explore this idea more and try to find out what are the contributions of land to atmosphere. So essentially, if you consider the water cycle is something like this. So this is essentially the water cycle. Of course, we are more interested in the big arrows. From ocean, we are getting moisture, it joins atmosphere, generates precipitation, groundwater flow, infiltration, runoff, and then joining the ocean. But what is also happening is that over the land, there is a lot of evapotranspiration that is taking place from vegetation as well as from water bodies. And this is what, of course, it's a small arrow. And also we normally don't give much weight to this evapotranspiration. So evapotranspiration is always given less weight. And because of, in terms of rainfall generation, and because of, at least for the monsoon regions, and that's one of the reasons because of which we never given much weightage to the land atmosphere interactions in the Indian monsoon region. So let us first quantify what is the role of this evapotranspiration to the rainfall generation process. So before going to that, let us try to understand, a little bit of what exactly done by soil moisture atmospheric feedback. So it is also a land atmosphere feedback. So this was one of the paper, which is a very famous paper by one of the very famous scientists, Sonia Seneviratne, of ETH Zurich. So she wrote a very nice paper on soil moisture atmospheric feedback. And so this is something which is known to us. So let's say this is the field capacity of soil moisture and this is the critical soil moisture. So when the soil moisture is above critical, so there is no limit there. It is not a water limited condition, but it is an energy limited condition. So given the energy, it will actually generate a lot of evapotranspiration. But as soon as the soil moisture goes below critical, it is a soil moisture limited condition. Depending on soil moisture, the evapotranspiration will be generated. It may not be strictly linear, but in many of the cases we consider them linear. And when the soil moisture goes below wilting point, permanent wilting point, then the plant cannot extract moisture, and because of which the evapotranspiration will be zero. The soil moisture goes like this. So essentially, if you look into this kind of flow chart, when soil moisture decreases, of course, the evapotranspiration will decrease. So red means this results into this. Soil moisture decreases means evapotranspiration will decrease. But when evapotranspiration will decrease, that means your soil moisture intake, the moisture intake from soil is actually reducing. When it is reducing, this will actually help in having more soil moisture. So again, it has a blue connection. So these are essentially known as kind of a feedback loop. Soil moisture has feedback on has impact on evapotranspiration, and evapotranspiration also has feedback on soil moisture. Now let's say if evapotranspiration decreases, when evapotranspiration decreases, your latent heat flux decreases. That means because of evapotranspiration, we need heat, and that heat is taken from the temperature, air temperature. But when evapotranspiration decreases, the temperature is not getting reduced because of the supply of latent heat flux, and because of this, your temperature will increase. So when evapotranspiration decreases, your temperature increases. But when temperature increases, that results into again increase in evapotranspiration. So temperature increase and evapotranspiration decrease, they are negatively related. So temperature increase will result into increase in evapotranspiration. And this is the way the forcing and feedback loops are formed and they maintain the cycle. So on other hand, if we just ignore this part, let's say evapotranspiration part, then we cannot really formulate in properly the temperature part. In fact, there are very recent papers that shows that if you increase your irrigation, that results into more evapotranspiration, and that results into decrease in the heat waves. So there are a lot of things which are actually interconnected with each other. And for understanding the water cycle, or for understanding monsoon, or for understanding any processes, we need to understand all of this component in a proper way. So that is something which is very important. And this message was initially given in 2010 by the famous Sonia Seneviratne's paper on soil moisture atmosphere feedback. Now, for this work, we are thinking of this kind of key hypothesis. We know that our monsoon is not properly simulated by the models. There is a huge dry bias. So the idea here is that, let's say, if you understand very well the regional land surface representation, or if you understand the regional land surface processes and improve that representation in a regional land atmosphere model, will improve the dry bias which we are getting in the operational monsoon model. So what we are trying to say, improve the land component of the land atmosphere model and see if that results into an improvement in monsoon simulations or not. And so essentially, when you're talking about moisture transport, for any case, there are two components of moisture transport. So essentially, we're talking about monsoon. It is all about moisture transport, and transported moisture has two components. One is advective moisture. So let's say if you are considering of Indian landmass. So from Indian, if you're talking about the rainfall over Indian landmass, one source of moisture is that is coming from the ocean. The other source of moisture is that is coming from land. That means rainfall is taking place over Indian landmass. The water reaches the soil gets recharged, plants take that moisture, evapotranspirates, it goes back again to the atmosphere and again gets precipitated, and that is known as recycled precipitation, because the same precipitation that's first precipitated over land and get evapotranspirated and again gets precipitated. So that is known as recycled component of moisture or recycled precipitation. So to understand, let's say if you really need to attack this hypothesis, the first thing is that how to really quantify the recycled precipitation. And for that purpose, so one of my student, Amay Pathak, started looking into it from 2011, 2012. And so when we search the literature, what we have found is that there is a very nice paper by Dominguez et al. Francina Dominguez, who was a student of Professor Praveen Kumar of University of Illinois Urbana-Champaign, she developed a very nice model on quantifying the land contribution to precipitation anywhere. So essentially, if you see, this is the atmospheric water budget equation, and if you apply a Lagrangian approach in computational fluid dynamics, something what is known as Lagrangian approach. Lagrangian approach means, let's say somewhere precipitation takes place. Where the precipitation takes place, you track the moisture, go back to its source and track the source. So this is the way you can actually find out what is the source of the moisture. So when the source of the moisture is coming from land, we call it as a recycled precipitation. When the source of the moisture is coming from ocean, we call it from advective source. So this is some sort of equations which she could derive. And Amay, my student Amay, who was my PhD student who graduated and is now an assistant professor at IIT Kharagpur. So what he did, he tried to apply it for Indian monsoon. He applied it for Indian monsoon, and there are certain interesting things what he could find. The first thing what he has found is that, so let's look into the second row, which talks about the recycling ratio. Recycling ratio means the ratio of recycled precipitation to the total precipitation. Now, if you look into it, you'll find that during June, the recycling ratio is very low. Why? Because during June, the soil is almost dry. The monsoon onset has just started taking place. So, of course, you can expect that. But down the line, July, August, and September, the soil gets fully recharged. The vegetation is fully grown. So, a lot of evapotranspiration is taking place. And because of which, your recycling ratio keeps on increasing. It reaches as high as 25%. So, you can imagine that over the Northeast India and the Central India, 25% of the moisture is actually coming from land, which is a huge amount, because Indian monsoon has a variability of only 10%. But here we are talking about 25% of moisture which is coming from land. And that tells us that, okay, probably during the initial part of monsoon is initiated by the oceanic moisture, but it is probably sustained by the land moisture. And during the end of the monsoon, it's very important. The recycled precipitation component is very important. Now, after that, we started collaborating with Francina, and Professor Praveen Kumar was Amay's external co-supervisor. So we all decided to apply this model for multiple land and oceanic regions. So let's divide the oceanic regions into multiple regions and land regions to multiple regions and apply the model with certain modifications and see what is happening. And this is what we wanted to see. And so we have got Central Indian Ocean, Ganga Basin. These are different sources. Red Sea region, Upper Indian Ocean, and Western Indian Ocean. So let us look into the Western Indian Ocean, that is the Arabian Sea. which is one of the major source of Indian monsoon. What we can see is that during June, its contribution is very high. But if you go till September, its contribution is becoming very low. Now look at the Ganga Basin region. Ganga Basin is a land region. In June, it's quite low. But if you go to September, you can see it keep on increasing. And in September, it's quite high. So that means the oceanic contributions are becoming decreases from June to September, and land contribution keeps on increasing during June to September. So Amay published it in Journal of Climate, and then we thought of comparing it for good and bad monsoon years, what is happening. So when you compare it for good and bad monsoon years, what we have found is that for good years, initially the oceanic contribution is quite high. So blue is the oceanic source and yellow is the land source, and black is the total precipitation where the scale is on the right side. So you can see here during a good monsoon year, initially the oceanic contributions are more. So our land is quite well recharged, because of which at the end land contribution is also quite high. But if you look into the bad monsoon year, initially the oceanic contribution is very bad, and because of its soil is not recharged, so it keeps on increasing and suddenly it drops because the soil doesn't have that much moisture to sustain the rainfall. So your soil land contribution drops, and as the land contribution drops, your total monsoon drops. So you can see that land contribution plays a major role over this region. You can see over this region the land contribution is playing a major role. So again, that again shows that at the initial part of the monsoon, it is initiated by the oceanic contributions, but it is sustained by the land contributions. Now, we again wanted to see, okay, we are talking about the land contributions to the mean monsoon rainfall. What about extremes? What happens to extremes? So we collaborated with one of my collaborator and very good friend, Dr. Roxy Mathukol of Indian Institute of Tropical Meteorology, Pune, and Amay, Roxy, and I, and few other co-authors, we all together worked on this. We wanted to understand that over this central India, there has been widespread extremes. That means over the entire belt, extreme event takes place. And these extreme events have increased, actually, what we have found over last 50 years. So what we wanted to find out that what are the major contributors to this extreme event. We thought that it will be all oceanic contributions, but what we have found is very interesting. We found that highest contributor is, of course, Arabian Sea, this region. And the second highest contributor is actually land, neither Bay of Bengal nor Central India, in Central Indian Ocean. So that shows that, okay, land is not only important for the mean rainfall, but also for the extremes. For the extremes also, land plays a major role in terms of supplying moisture to the rainfall processes. Now we'll again go back to our basic questions. We are talking about climate forecast system version 2, CFS v2, and we wanted to understand the bias. So let us try to see how to really understand this bias. So essentially, this is a different way of representing the rainfall. This is from the reanalysis datasets of ERA interim, which is the proxy to observed dataset, and these are essentially the rainfall bands. You can see this is 20 degree south, this is 0 degree, this is 20 degree north, and this is 40 degree north. And this is averaged over 70 degree east to 95 degree east. So 70 degree east somewhere to 95 degrees. So you can consider over this region, we have considered what is happening at 30 degree north, 0 degree, 30 degree south, and so on and so forth. So you can see here, initially the rainfall band is over the southern hemisphere. Now, as the monsoon starts, it moves towards the northern hemisphere, and over this region, the Indian region, it results into more rainfall. And here the rainfall is less, and again it comes back, the rainfall band comes back. But let's see what is happening in CFS v2. In CFS v2, it doesn't happen. So initially this part and this part is matching, but when it, in terms of the northward movement, what is happening is not moving properly. Here the entire thing has moved, and here it has not really moved. Rather, some part is moved. So it's some kind of a double ITCZ formation. So some part is moved and some part is here, and that results into dry bias. If the entire thing would have moved, then we would not have got a dry bias over the Indian landmass. But this is actually not happening, and because of which we are getting a precipitation bias. So one of my students, Sahana, who did this work and this got accepted in climate dynamics, but she has also explain the different multiple reasons because of which we are getting this kind of dry bias. Now what we tried to do is that we tried to apply a regional land atmosphere model, which is weather research forecasting model or coupled with a community land model. So what we wanted to do is that okay, let us take the CFS version 2 output, which is the global model output, apply it to a regional model of weather research forecasting model, community land model, or CLM, with a better representation of land at a finer resolution. Let's run the model and find out if we are able to remove this dry bias or not. So I asked one of my students, Anjana Devanand, to really do this work. So she started working on this. So for those who are new to this WRF CLM, just giving you an idea, WRF is a regional atmospheric model. So it's a very complicated model. I'm not going into details, but it sends precipitation, wind, temperature, pressure, and so on to the land model. So land model has a standard land surface models and a detailed vegetation model. So in this case, we are considering a prescribed vegetation, not really a detailed vegetation modeling. We haven't really done the vegetation modeling, but we have considered a prescribed model. And from the land model, it sends you latent heat flux, sensitive heat flux, moisture flux, and so on and so forth. So, and when we are running WRF and CLM together, we run the entire thing together. So what we did, vegetation was prescribed, constant over a period, but we have considered like this. So this WRF CLM was run for 15 to 30 years, and then we wanted to see if the dry bias has been removed or not. So this is the WRF CLM simulations which Anjana performed. So Anjana wrote this paper in Geophysical Research later, and her work was selected as the research spotlight of American Geophysical Union. So what she did here is that she considered this zone and ran the WRF CLM. So this is essentially the IMD dataset, India Meteorological Department dataset. And this is the original bias. You can see the dry bias which is there. But as soon as you are running a WRF CLM, what you are finding, so we are focusing more on the Ganga basin. We have presented a land, we are focusing more on the Ganga basin with a better land representation of Ganga basin. And this is the region where the recycled precipitation or land atmosphere feedback is quite high. And what you are finding is that you can see over the Ganga basin region, the dry bias has been reduced. So from minus 4.822, it becomes minus 1.81. So from 68% dry bias to 25% dry bias, it has reduced quite significantly. And we are quite happy, but we wanted to make sure it should not be a model artifact. So let's try with another land surface model and see if the same thing we are getting or not. And we are finding even for the other land surface model, we are getting higher reduction in dry bias. That shows that if you have a better land model and couple it with a better land model, your dry bias is getting reduced. So we wanted to see with other data products, are they consistent or not? And we are finding they are quite consistent. If you can pick up any data product and check, it is actually happening. So your dry bias is getting reduced when you are using a regional land atmosphere model. So why it is happening? Of course, one of the reasons should be your land recycled precipitation is reducing. So let us try to understand what is happening. So there is the original model, which is the operational model CFS V2, and we apply again the recycled precipitation concept. And what we try to do is that we try to find out different contributors. So if you see the green one is the land contributions. Sorry, the blue one is the ocean contributions, and the red one is the land recycled precipitation. So what you can find is that from the oceanic contribution, from the land, there is a huge huge dry bias. So that means land contributions in CFS V2 is underestimated, and at the same time the oceanic contributions are also underestimated in CFS V2. Now when you are running WRF CLM, as expected, you are finding that your recycled precipitation has improved, so your land contributions are improved. So the the bold line is coming from the observed data, and the dotted line is come from the model simulations. They are actually matching, which was not matching in the CFS V2. But when you are running WRF CLM, they are quite well matching. But another interesting part is that even during the onset part, the land contributions are also matching. So is that a magic? Because you are improving your ocean, your land land representation, but what results into the good match for the oceanic contributions? So we wanted to understand what is happening. Then when we again looked into it, what we have found is something interesting. It's actually all about better representation of Himalayan orography. So what is happening in CFS-B2 is something like this. That is the operational model. Your land, Himalayan country, Himalaya is not properly represented, because of which the extratropical is a colder region. The colder region is actually, the wind from colder region is actually entering into the Indian landmass, and that makes the Indian landmass cooler. Now, if you're talking about monsoon, during the monsoon, for a better monsoon, we want a warm land and cooler ocean that results into transport of moisture from ocean to land. But as this cold wind from from the extratropical regions, it enters in the model, because of poor representation of Himalaya, that results into a cooler land over the Indian region, and that results into dry bias. But when you're considering WRF CLM or WRF NOAA, Himalayan representation is quite good. It doesn't allow the extratropical wind to enter Indian landmass, and that makes the Indian landmass warm, and that results into a better oceanic contribution. So with your land improvement, you are not only improving the recycled precipitation component, but also your oceanic contributions as well. So this is what we have found. Then so Anjana wanted to go another step. So he wanted to see, look, we are talking about the natural condition, but what is happening over the Indian region? There is lot of human intervention that is taking place in terms of irrigation. So of course, over the last few years, the irrigation has increased quite significantly. The other part is that if you consider any kind of Western models, if you pick up any model like variable infiltration capacity model, or community land model, or NOAA land surface model, all of them are designed for Western crops. So they are not really designed for paddy. They are not really designed for Indian irrigation. Indian type of irrigation doesn't really follow soil moisture monitoring. It just uncontrolled irrigation, flood irrigation, paddy like condition where your crop field is actually in submerged condition like this. So these sort of things were never considered in any of the land surface models. So if Anjana has to consider the irrigation feedback to the atmosphere, she had to first consider the contributions from irrigation to land, from the atmosphere. And for that part, what she had to do, she had to uh, develop a new module in WRF CLM, which can take care of Indian type of irrigation as well as the paddy irrigation field. So both the things she has to consider. So what she considered, she had done some experiment. First one is the control simulations where there is no irrigation and no paddy field. The second one is realistic irrigation, that means Indian irrigation type and paddy fields. And third one is idealistic irrigation, that means when your soil moisture is going below permanent wilting point, you recharge it till field capacity and stop and check what is happening. So it's idealistic irrigation that will save a lot of water, and this is the real irrigation. And if you consider real minus ideal, you can see how much water we are actually wasting in terms of irrigation. But that's a different story. That is not today's topic. But actually it shows that there is a lot of difference. If you do a idealistic irrigation or Western models, if you simply pick up and blindly run them, they will consider this sort of irrigation or no irrigation at all. But what is happening in India is entirely different. Hence, for any model, we have to be very careful to be applied for Indian condition. Now, this is the irrigation for paddy field, which was kind of a very complicated thing, because when you're talking about paddy field, your your energy balance, your water balance, everything gets changed. So you have to really consider in a different way. So Anjana has Anjana has developed a specific paddy irrigation module in WRF CLM, and then started applying. So these are actually online available. All these codes are online available, and anybody wants to do the experiment, they can do it. Now what she has found is very interesting. What she has found is that if you consider a Indian irrigation practice, you will find that the rainfall band over the September is moving northwest, which is not happening in ideal irrigation. So essentially it shows that if you go for uncontrolled irrigation rather than a proper controlled irrigation, your rainfall band is actually moving in other directions. So on the land, if we change our water management practice, that has the potential to shift the rainfall band, which is which is sort of a very new finding, and Anjana published it in again geophysical research later. And this is something as schematics or cartoon that shows that when you are doing some kind of paddy irrigation and groundwater pumping and so on, it shifts the rainfall band over this region. But if you have a controlled irrigation, it is actually falling over central India. And this is what is very important, what she has found. And there's a first time where researchers have started mentioning, look, if you change your management practice over land, that has the potential to change the atmospheric processes. And so this is some kind of a explanation that shows that how it has been changed, and it shows that it is associated with the change vertical integrated moisture transport as well as changed in equivalent potential temperature. I'm not going into details of this, but it shows that, look, if you change your irrigation practice or water management practice, that results into, that has the potential to change the atmospheric processes. Now this is, sorry, yeah, this is one of the things where we're talking about water management. The other thing is related to land use land cover change, and I'm not covering all the land use land cover change, but I'll quickly go through some of the urbanization related things. So when you're talking about urbanization, that is another very important land atmospheric feedback processes. So urbanization, one thing of course we know is that urban heating. So if urban is getting heated up, because urban temperature is quite high, and because of which it has more moisture capacity and more rainfall. Second one is, so I'm trying to say that in what way urbanization can affect rainfall. The second one is urban heat islands. That means urban has a higher temperature compared to the nearby non-urban region, that results into wind flow and rainfall generation. Third one is urban regions produce a lot of aerosols, which are essentially the condensation nuclei. And the fourth one is the urban structures, eddies and instabilities results into more rainfall. So I'll again go back to one of our paper which published in 2013, where we have shown that if you consider last 100 or 113 years of monsoon rainfall data, if you consider the first 50 years and second 50 years, you'll find that there is a very little similarity among the trends of first 50 years and second 50 years. So the question what we raised in that paper, this was done by one of my student Vittal, and Professor Shubhankar Karmakar from Environmental Science was the lead author for this work. And what we have found is that when there is a change in the trend from before 1950 to after 1950, what may be the reason behind it? And what we have found is that urbanization is one of the reasons, because what we have found is that, let's say if you do a change point analysis of the extreme rainfall over 100 years and find out where exactly the change point has really occurred. And what we have found is that if you consider the urbanized region, in the urbanized region, the change points are actually mostly after 1975. So in majority of the urban regions, the change point is year 1975 or after 1975. And our urbanization intensified after 1975. That shows that the change in rainfall and the change point which we are getting after 1975 over urban region, they have a close relation. And that shows that probably urbanization has played a major role. So after that, my other student Hitashri Sastry, who was also the first graduate from interdisciplinary program in climate studies, so she did a detailed analysis on impacts of urbanization on Indian rainfall extremes. What she has found first is that over the central region and the southern region, the impacts of urbanization is quite prominent. Whereas over the northern regions, it's very difficult to find out from a gridded data what is happening. Of course, we need a station level data, but from gridded data, even it's quite visible that if you consider the central and western region, the impacts of urbanization is quite prominent. And this has actually increased in the very recent period. So what she has found is that the impacts of urbanization on rainfall extremes, they are more prominent over the recent period. That shows that in urban regions, the the extreme rainfall has increased, where in non-urban regions and in the nearby non-urban regions, such increasing trend were not really formed. So this one Hitashri published in Journal of Geophysical Research, and then she wanted to do some specific statistical experiment to understand what is happening. So what she did, she picked up two regions. One is Mumbai and second one is Alibag. Mumbai is highly urbanized, we all know. Alibag is very close to Mumbai, and it is having almost similar geographical condition. But Alibag is a small town. It's a kind of a rural or semi-rural area. So what we wanted to find out, given the large scale circulation pattern. So for Mumbai and Alibag, they are very close to each other. So they may have similar kind of large scale circulation pattern. So given the large scale circulation pattern, given same large scale circulation pattern, are we getting changes? Are we getting similar kind of changes in extreme rainfall over Mumbai and Alibag, or are we getting different kind of changes in extreme rainfall over Mumbai and Alibag? This is what we wanted to find out. So what we did, we first tried to find out what exactly is the large scale circulation pattern that results into extreme precipitation. Sorry. So what we did, we performed a cluster analysis and found out what are the different clusters that exist in the atmospheric circulation over Mumbai and Alibag or over the larger region. We found there are 4 clusters really exist as per statistical clustering techniques, and what we have found is that cluster one specific cluster of atmospheric processes that results into extremes over this region. And what we have found is that from 1969 to 1988 to 19 this should be 1988 to 2010. So what we have found is that in the second half such a cluster has actually reduced, but the extreme precipitation in Mumbai has increased. So that shows something is happening. So what we did, let's look into this figure. We don't need to look into those figures. So essentially what we did a quantile regression analysis. In the quantile regression analysis, we wanted to find out, given the same circulation pattern over Mumbai and Alibag, and given the same circulation pattern for the 1969 to 1988 period and 1989 2008 period, what are the quantile regression values, different quantile regression values. So given the cluster 1 kind of classes, which is responsible for extreme rainfall, what we have found is that for the Mumbai region, this is for Mumbai, the 1989-2008 higher quantile rainfall is quite high. Given the 99 percentile is very high, but is Alibag is actually opposite. You can see it has actually reduced at 99, but in Mumbai 99 has increased quite significantly. That shows, even a rigorous statistical analysis also says that given the circulation pattern, the extremes are more increasing in urban regions compared to non-urban regions. Now this is the last part of my talk. Here we are trying to say is that yes, urbanization not only increases the extreme rainfall, but it also increases the spatial variability within the city. This is very important. Those who have come to Mumbai during monsoon, or those who stay in Mumbai, they know that if you go from, let's say, Mumbai airport to the Navi Mumbai region, probably in the Powai region you will receive high rainfall, then little bit of low rainfall, then in the Eastern Expressway you will receive very high rainfall, then again low rainfall, and so on. So there is a huge spatial variability. One of my students, Shupanta Pal, wanted to understand what is the reason behind the spatial variability. What we did, we ran a WRF at a very fine resolution, at 1 kilometer resolution. So we started with 27 kilometer, 9 kilometer, 3 kilometer, and move over Mumbai 1 kilometer. And what we wanted to find out is that, let's say we run the model with no urban canopy. We have not really considered urban canopy in a proper way. Then second case, what we have considered, we considered urban region means it's with a fixed height urban layer. The third one is multi-layer urban canopy. So what we considered, we have high-rise buildings, we have slum areas, we have roads and everything. And then we wanted to find out what sort of differences we are getting on extreme rainfall days. So we have applied to some of the 2014 extreme rainfall days, and what we have found is that if you consider multiple layers of urban canopy model, the values are actually quite similar to the observed rainfall. But if you consider the single layer or no urban canopy model, they are actually not matching. That means this actually results into correct values or more similar values with observed rainfall, and these two are not really able to simulate that rainfall. That shows that even a smaller changes in terms of urban canopy that also have potential to change the rainfall values. Now, so, and what we have found, so in Mumbai has now distributed rainfall monitoring stations. So we collected these stations from 2014, and we're finding that if you consider the multi-layer urban canopy model, this actually results into good simulations over the regions. Then this is the most important thing. Now look into this figure very carefully. So you can see the blue line. The blue line is essentially the observed spatial variability of rainfall on that specific day, on July 11th. This is the blue line. Now, let's say if you don't consider the urban canopy, it is actually producing this kind of spatial variability. That means the spatial variations is quite low. You can see it is coming here. Now, if you consider the single layer urban canopy model, it is coming like this. Only when you are considering multi-layer urban canopy model, they're actually matching quite well. And you can see in terms of spatial variability also, this is the observed, and the no urban canopy mod, sorry, this is the observed, this line is observed, this is with no urban canopy, this is single layer urban canopy. They are not able to model the spatial variations, but if you consider multi-layer urban canopy model, it's actually able to produce the spatial variability. Even for this one also, you can see that this one is matching with the dotted line. That shows that, you know, multi-layer urban canopy model is important to understand the spatial variations of monsoon rainfall. And at the same time, what is happening, let's say if you don't have urbanization, you'll get the rainfall distribution like this. But when you have urbanization, that results into these sort of things. So essentially, you can see these are different buildings. Let's say the wind has to flow. So if there is no building, wind will flow just like that. But if wind has to flow in between two buildings, it has to form a channel, and that results into lower area, higher velocity, higher non-stability, or atmosphere becomes more unstable. At the same time, there will be a lot of eddies that will form, and that results into more instability and more rainfall. And this is what is happening, and that results into generation of few pockets where the rainfall is intensified. And you can see that if you introduce urbanization with multi-layer urban canopy model, your spatial variations are increasing. So this is getting flattened, and which is having a higher tail. That means more extreme rainfall at few pockets. And this is what happens. In fact, very recently, when we have rainfall, extreme rainfall over Mumbai, you can see that the southern Mumbai region receives very high rainfall. It received a very high rainfall compared to the suburban Mumbai region that didn't receive that much high rainfall. So that shows that it has higher variability. And what you find is that, if you go beyond 5 kilometers, the rainfall actually decorrelates. That means the rainfall of one region becoming non-correlated, the hourly rainfall of one region is becoming uncorrelated with another station. That means every 5 kilometers, or at least every 10 kilometers, we need at least one station in an urban region to really understand the spatial variations. So, and that results into, because of the generation of pockets and instability. That shows here, actually, this is with multi-layer urban canopy model. You can see that there are lots of reds and blues, two extreme conditions which are happening. That means generation of pockets and more instabilities over this section. And that shows that this is actually very important to consider multi-layer urban canopy model. So to conclude, I will not list the conclusions, but what I'd like to mention is that if you're considering any earth systems, there are multiple variables which are connected to each other by links. And if you perturb one of them, that results into perturbations in other variables through links, and the earth system will change its state from one to another. And if we really need to understand the dynamics and trajectory of earth system, we should not ignore any of the processes. Like land process was ignored for monsoon system, but now we can understand that land process is important. So we should not ignore any of the system. Rather, we need to understand that what is the capability of the perturbation of that single variable that can affect the entire system, and when it will get dampened. That's what is very important to understand the earth system processes. So thank you very much. And all the works have been done by students, and I'm really thankful to all my brilliant students who teach me newer concepts every day. And thank you for all your patience. Thanks.
Thank you, sir. Thank you so much. Since now we are already short of time, we have some 4-5 questions.
Yes.
We can take them. 1 second, sir.
Sure. Yes. So the first question is, why land atmosphere interaction is strong over Ganga Basin? This is because Ganga Basin is one of the most fertile region of Indian region, one of the most fertile Indian region, and so essentially that results into more evapotranspiration. That's the first thing. So the flux that is coming from land to atmosphere is quite high. The second thing is that Ganga region is not very close to the ocean. So essentially, if you consider southern regions, they are very close to the ocean, but Ganga region is quite above. So it's actually towards the northern side, close to the Himalaya. And that results into more kind of a close circulation, and that results into more strong land atmosphere interactions. Yes, while the evapotranspiration component might be quantitatively low, does it nevertheless have an important role in regulating regional local rise spells? Yes, exactly. That's what I have shown. So evapotranspiration component can be low, but it has the potential to change the monsoon processes, and that is what I've shown that, so essentially these processes have the potential to change the large scale circulation pattern, even the position of the high rainfall bands. Why do we see coupling GCM models behave differently over different surfaces, mainly surfaces between model results and modules? So I'm not very sure what does it mean. What do we see coupled GCM models behave differently over different surfaces? Okay, so probably you are trying to say is that, the models have shown higher rainfall over ocean and lower rainfall over land, and one of the reason could be that I have mentioned that so essentially, for a proper distribution of rainfall, the temperature has to be properly simulated. When temperature is properly simulated, then the thermal contrast will drive the atmospheric circulation that will take the moisture. But what is happening in CFSV2, what we have found that through Himalaya, a lot of wind that is coming from extratropical region to the Indian landmass, that makes the Indian region cool. And when Indian landmass is cold, the moisture transport from ocean to land is not taking place properly in CFSV2, and that results into dry bias over the land and wet bias over the ocean. Yes. Any more questions?
Yes,
How
sir.
will
Two more
you
questions, sir.
how will you differentiate between MISO? No. MISO and MISO and MJO, they are different. MISO is essentially which is going from south to north, essentially southwest to northeast. They are essentially some sort of a wet rainfall band followed by a dry rainfall band. But MJO is different. MJO is over equatorial Indian Ocean that moves from west to east. They are also high rainfall band followed by low rainfall band, again followed by high rainfall band, and so they are different. How remote sensing data can be helped in tracing the land atmosphere interaction? Of course, remote sensing data is important, but ground truth verification is also important. So remote sensing data is important in terms of understanding the vegetation condition, the evapotranspiration, the soil moisture, and everything. Because if you have a better monitoring of them, then they can be assimilated very well into the land atmosphere model, and with that you can actually improve not only the land simulations but also the atmospheric simulations. Yes.
Right, sir. Due to time
Thank you.
constraint, we picked out only 5 questions. Thank you so much,
Thank you.
sir. Thank you
Thank you
very
very
much.
much. Thank you.
Thank you.
Thank you.
And
Stay safe.
thank you to all participants also. We'll see you tomorrow. Thank you so much for attending.